Możesz tutaj stanąć, żeby Cię było widać. Nie możesz powitać wszystkich i zaprosić.
Hello everyone, welcome to our last day of talks, and our first speaker will be Himanshu Verma from the Indian Institute of Technology, and he will tell us about astrometric microlensing of primordial black holes with Gaia.
Yeah, hi, am I audible?
Hello, can you share your screen?
Yeah, sure. Let me know if you can see my screen.
We can see your desktop, but okay, we see your presentation now.
Okay. Okay, so shall we start now?
Yes, please.
Yeah, okay. So hello everyone, this is Himanshu Verma from Department of Physics, IIT Bombay, India. And today I'm going to talk about astrometric microlensing of primordial black holes with Gaia, which is based on our recent work, which we archived recently. So what is we have and what is the main goal of our work? So it is basically based on the fact that Gaia is going to provide us more than 1 billion trajectories of galactic and extragalactic sources. Another fact is that the primordial black holes are one of the candidate of dark matter, which we know that it is like most of the stuff in our Milky Way is dark. And we know that there is a phenomena called astrometric microlensing, which can alter the trajectories of these sources, which will be observed by Gaia. So we asked this question: what if we can kind of distinguish the astrometric microlensing signals of primordial black holes, which can induce shift in the trajectories, which will be observed by Gaia? And so in our work, we basically estimate the astrometric microlensing signal rates due to primordial black holes. And we finally give projected constraints on primordial black holes that will be established by Gaia telescope once the time series data will be out. And at the end, I'll summarize. So starting from what are the main information that we used from Gaia is the first is due to the fact that Gaia has this special scanning law over the whole sky, and so that basically has these two telescopes, and it basically spins, and that spin axis presses about the line joining from the telescope to the sun. And due to this special scanning law, at the end, each telescopic arm observes each patch in the sky on an average once in a month. Another fact is that if you average out over both the telescopic arms, in that case, what you will have is that each source, like more than 1 billion sources, will have 35 individual positions separated by on an average 52.2 days. So that will be after 5 years. Sorry. Yeah. And the accuracy in the position measurement would be something like 0.076 milliarc second for stars brighter than 14 magnitude. So this is the first information that we use, which is basically what is the sampling scheme. And the second information that we used about Gaia is how the uncertainty in the position measurement changes as the brightness of an object changes. So it's the black curve, which is the observed uncertainty in the angular position of the source, and which basically depends on the apparent magnitude. All the dash curves are basically the simulated one, but what we use in our work is whatever is observed for according to the EDR3 catalog. So we took these, this basically empirical fit of this uncertainty model, which is based on 34 months of observation of Gaia. And what it actually observed is, I mean, whatever the catalog that we have for the 34 months, of course, now we have the R3 as well. But what we use is the EDR3, early data release of the third version. And this is the catalog of the stellar population, depending upon what are the characteristics of the sources. And because in the lensing calculations, there are only these 4 source characteristics that we consider. So we use only 1.43 billion sources out of 1.8 billion stars, for which we have a good estimate of the distances. We have a good estimate of the galactic alpha and delta, and as well as the apparent magnitude. So the third information we use is this catalog. And we ask this question: out of these sources, what if the trajectories of these sources will be affected by because of the presence of primordial black holes? So let me quickly introduce what this expectation of primordial black hole is in our Milky Way. So we know that in the very early universe, there are some fluctuations in the universe, and those fluctuations, if they have excess density enough, then they can collapse and form these black holes. So their formation is like primordial. It's not the stellar formation of black holes. And if those formations have been happened, then those primordial black holes will be a candidate of dark matter today. So even within our Milky Way, we expect that if those PBHs are there, there will be a fraction of dark matter which will be in the form of primordial black holes. So that fraction is plotted on the right panel on the vertical axis, and on the x-axis is the mass of the primordial black holes, assuming monochromatic mass functions. So what you are already seeing here is the colored region, which are already excluded with various experiments, including the blue one, which is the photometric microlensing. And what we ask is how the astrometric microlensing of primordial black holes with Gaia will set up a constraint on this parameter space of primordial black holes. So let me quickly introduce what is this astrometric microlensing. It's basically the shift in the trajectory that you observe because of the presence of the lens at the center, which you are seeing on the upper panel. So if you assume that the trajectory of the source is straight line, but because of the gravity of the lens, what you observe is a distorted trajectory of a source. So that apparent distortion is basically called the astrometric microlensing. But there is the magnification in the brightness of the source, which is color coded here with the colors, and that you can see that as the source moves towards the lens, the magnification increases, and as it goes away from the lens, the magnification decreases. But on the other hand, because what you see is kind of a magnification weighted two images, and if the source is very close to the lens, then on an average, the overall strength of the signal, which is the apparent shift, that reduces. So that's what you're seeing on this lower panel. Now this apparent shift it depends on two things. One is what is the instantaneous angular separation between the source and the lens, and there's a scaling here which is called Einstein angle, which depends on three parameters: what is the mass of the lens, what is the distance of the source, and what is the distance of the lens from us. So typical for the typical values of mass and distances, what we get is Einstein angle of the order of 2.854 milliardsecond. So with this astrometric and photometric phenomena, if you compare how the signal varies as you increase the separation between the source and the lens, then the blue one is the astrometric microlensing signal, which you can see that it lasts longer than the photometric microlensing. And hence, we expect that the astrometric microlensing will have larger cross-section as compared to photometric microlensing. Just for the visual effect, we can clearly see that if you have multiple trajectories at different distances, the trajectories, which is like after the blue blob trajectories, you can't see any magnification, but the shift in the trajectory is still significant. And that shift is plotted in the lower panel, which you can see that is above 0.25 milliarcsecond. And as I told you, the Gaia is going to give us a position measurement up to 0.076 milliarcsecond. So certainly this kind of source lens system will definitely be distinguished by Gaia. Now, specifically for the primordial black holes, because we expect that their masses can range from something like 10 power minus 18 solar mass till something like 10 power 9 or 8 solar mass, depending upon where you expect the dark matter. So what we do is we kind of categorize these astrometric microlensing signals depending upon a quantity called duration of the event. So how do we calculate? So basically, we know that from the center of the lens, there is a region which is this green shaded region where a trajectory has to lie in order to give a significant shift in the trajectory so that Gaia can measure. So we calculate what is the duration for which a trajectory would be in the green region. And that duration depends on these 5 parameters. The initial mass and the distance is for the lens, and the velocity is the relative velocity of the source and the lens, and ds and mg are the distance and the apparent magnitude of the source respectively. So what we do is we take all the possible combinations of these parameters and calculate these event duration. And if event duration is less than the sampling time, that means the measurement of the position, the time between the measurement of the 2 consecutive position of each source, if that is less than sampling time, if the duration of the event is less than the sampling time, then we call this as a short duration lensing event, and we declare that there will not be any observable lensing signal detected by Gaia. And if this event duration is greater than sampling time and less than the nominal Gaia observation period, which is, let's say, 5 years, which is already crossed, of course, then we say that it is intermediate duration lensing event. And for that, we declare an observable, which is whatever is the maximum shift that Gaia will observe during the whole observation of the trajectory. And if the duration of the event is greater than observational period, then it will not observe that peak in the trajectory. And that is why what you will observe is just a part of the trajectory. And hence we declare an observable, which is the difference in the shift in the trajectory. So for all possible combinations of source characteristics and lens characteristics, we categorize the observables according to the event duration. And for ideally, which is intermediate duration lensing events, and LDLEs, which is long duration lensing events, these are the only possible types of signals that Gaia can observe for primordial black holes. So we calculate what will be the detection criteria, which is if this shift is greater than the uncertainty in the measurement of the position of the source, then we say that, okay, if the source is lying within that beta, which you can see, which is separation between the lens and the source, then there will be a detectable signal. So for ideally, this is the detection criteria that we used. And for LDLEs, again, it's the same detection criteria, but the observable is different now, which is the change in the shift in the trajectory. So for both of them, we calculated what will be the maximum separation between the source and the lens within which a source has to lie in order to give a detectable signal. And then by fixing the hypothesis of dark matter and for each star in the Gaia catalog, we calculated how much region a lens will sweep in the sky so that we calculate what is the probability that it will lie in that detectable region. So at the end, what will be the probability of observing these astrometric microlensing signal? That would be just the ratio of this yellow patches divided by the total area that we have taken. And then all we have to do is just calculate how many lenses are there in our line of sight. So we calculate this probability. So what I'm showing you is for one example of primordial black holes, which is fraction is equal to 1. That means all of the dark matter is primordial black holes. And if you assume that all of them have same mass, 14 solar mass, then for each different characteristic of sources, this is the distribution of the probabilities. This is just one example. Later, we change F and M for all possible values. And then, yeah, sure. And then, sorry, are you saying something?
I'm just saying you have 3 minutes left.
Yeah, sure. Yeah, so we took this probability and the whole Gaia catalog, which is the distribution of the sources, and we multiply to get number of lensing events distributed various characteristics of the sources. So this is what we get. And then we change the values of F and M with certain assumptions, which I'll just list down here. And ultimately, we get this exclusion on the parameter space of primordial black holes. So you can see that it can go as small as something like 3 into 10 power minus 4. And its mass can go from 0.4 solar mass to something like 5 into 10 power minus 5 into 10 power 7 solar mass. So this is the final outcomes of our prediction that Gaia would be able to set up on the primordial black holes. And another one of the interesting feature that you can see here is this yellow star. So if you assume that the all the LIGO observation black holes are primordial black holes, then this is the point that you need. So if Gaia exclude this point, that will exclude the possibility of LIGO have observed primordial black holes. So yeah, with this, I'll conclude. Thanks a lot.
Thank you very much for your talk, Himanshu. Are there any questions from the audience on the Zoom? Hello. Hello.
Yeah.
Can you hear me?
No. Come close. Maybe I do.
Yes.
Yeah.
Working. Okay, it's only one microphone that's working, I guess.
This is where the input is here, the camera. So if you speak close to here, you will be heard. Okay.
Okay, very nice talk. I have a question about the Gaia scanning law. Because you haven't considered scanning law, am I correct? Just the approximate gap in observations. Do you plan on adding that?
Yeah, so basically in this work, we have assumed a uniform scanning law that is separated by something like 52.2 days, which is of course kind of an average separation. In reality, there'll be gaps in the data, and the scanning, the sampling will not be a uniform sampling. So because here in this case, we don't kind of numerically simulate trajectories. So that is why in order to just get an estimate of these exclusions, we assume this simplified assumption. But in the next work, we are actually simulating different possible trajectories, and we are going to incorporate these sampling schemes, like the real sampling scheme. You know that this is also, I mean, the pointings has been kind of, I mean, published with the DR3. So we can use that in order to get the realistic, more realistic calculations.
Okay, thank you very much.
Yeah. Thank you. Thanks a lot.
Okay.
Why? I will shout. There is a question on Zoom. Why set the mass of PBH to 14 solar masses? But I think that was just an example. But anyway, Himanshu.
Yeah. So that 14 solar mass basically lies at the maximum sensitivity region. So the plot that you are seeing on my screen, I hope, it goes deepest if you consider mass is equal to 14 solar mass. So of the order of 10th of solar mass, the sensitivity of Gaia would be maximum. That is why I was just showing you examples for that. Otherwise, for each different values of F and M, you will have the same distribution of lensing on the sky.
Okay, thank you very much once again, Himanshu. And our next speaker will be Algita from Warsaw University Astronomical Observatory, and she will present her talk about probability of detecting black holes via NaCo adaptive optics.
Hello, do you hear me? Hello, good morning, everyone. So my name is Algita. I'm a PhD student at the Warsaw University in Astronomical Observatory, and today we're gonna storm the more like instrumental part. So today I will gonna speak about adaptive optics mostly. So the first would be like why we need to detect black holes. Of course, there were a lot of, let's say, previous speeches about black holes, and actually right now, of course, the universe is so complex and so interesting, but how to say, majority of the unknown, let's say, unknown properties and unknown, let's say, detections are based on the black holes. So, and one of the, how to say, very interesting methods to detect black holes is the gravitational microlensing phenomenon, because it relies on the, how to say, our object and then the lens in the object passing by, and it's due to Einstein's gravity, it bends the light rays and it forms some sort of a curve. And here you can see when we have let's say a black hole nearby, so we can see the another peak in our brightness curve over the time. And moving forward, why we need adaptive optics. So adaptive optics, I would say, one of the most, let's say, complicated optical systems. And nowadays, not only for the astronomy, but for the other, how to say, applications as well. Because when we have, let's say, space-based telescopes, we don't need to get rid of atmospheric turbulence. Of course, space-based telescopes are not that large in diameter. The majority, I mean, James Webb, it's only 6 meters, while the biggest nowadays ground-based telescope is 12, and there will be even more and more, 30 and 40 meters diameter. And that's, but the main issue of ground-based telescopes is the turbulence. And turbulence is not only the, how to say, whirlpools of the air and clouds, but a very complex system which has different types of atmospheric layers with different temperatures, with different wind speeds and wind directions. And that's why nowadays the biggest, let's say, ground-based observatories are equipped with adaptive optics, and not only with one system, but even the few. And the main, the main objectives of adaptive optics system is deformable mirror, which consists of actuators. Actuators are some sort of like sensors who are adjusting itself by itself on your perturbed wavefront, because the most important thing is that your photons have aberrations, so you have blurred image without adaptive optics. That's why deformable mirror with actuators, it transforming itself due to the shape of the wavefront. And of course, the wavefront sensor, most importantly, Shah-Hartmann. Of course, there are many different types of wavefront sensors, but the majority of observatories, they use Shah-Hartmann's. So Shah-Hartmann's, the main issue, the main objective is that they have arrays of microlenses as well. We call them also microlenses, and they are compressed in a very small aperture, because building a big aperture Shah-Hartmann wavefront sensor is kind of an issue for the engineers. That's why, let's say, that's why normally they use beam expanders instead of building a large aperture wavefront sensor, or even placing 2 or 3 of them, depending how many atmospheric layers they want to, get rid of. So here you can see, when we have adaptive optics system, we correct the perturbed aberrated wavefront into a plane wave. I mean, approximately into a plane wave. VLT, or Very Large Telescope, they also had, because it was decommissioned a couple of years ago, NaCo, or Naismith Adaptive Optics System. Now, of course, the predecessor is Sphere, because it had a lot of problems due to Shah-Hartmann wavefront sensor, because the micro lenses, when they are compressed, they're degrading due to the temperature, electricity, and etc. So as you can see, we took the images from NaCo, and you can see there's like many, many disturbances. They're not very clear images. So we had, let's say, 5 target stars, and I just presented J-band. So we also have in the K-band. And what is the most important thing for the person who works with, let's say, adaptive optics? So the majority of people wants to, let's say, to know the PCF of point spread function, because point spread function gives the information about your, your objective, not only about your wavefront. Wavefront, of course, but normally with a Shah-Hartmann wavefront, you don't detect the wavefront, you detect the derivative of the wavefront. So what we did, we used Tristram and Riesto paper, who determined the point spread function exactly for the NaCo system. So here you can see we have the point spread function and the fitting. This is so-called the 3D view. And then let's say we took all the brightest stars, let's say, of course, without all those disturbances from the instrument, because this is mostly caused by the instrument. That's why it was decommissioned. And let's say we plotted the probability to detect, let's say, a possible black hole nearby, because as you can see here, we don't see another peak here. So that's why we don't know if it's a black hole or not. But of course, for instance, in the future, if we will use ELT, Mikado system or something, normally the resolution or thrill ratio will be approximately to 90%. So it's mostly like a stream adaptive optics, because it's not only single conjugated, but multi-conjugated, because there will be different layers of atmosphere getting rid of. And there will be not only just one wavelength sensor, but a few or a lot of them, depending on how many laser guide stars there will be, and how many layers of atmosphere they will be getting rid of. So, and that's it. I don't want to take a lot of time, and thank you for your attention.
Thank you very much, Algita. We are a tiny bit behind time, so we probably have time for like one quick question. Anyone? Questions on the Zoom?
No.
No? Okay, thank you very much once again, Algita.
Thank you.
And our next speaker is Etienne Bachelet from Institut d'Astrophysique de Paris. And the talk title will be Results from the Omega Key project. Yeah.
Thank you. I will share my screen. Everyone sees how okay?
Yeah.
Yeah, okay. So thanks for the invitation. And today I would like to discuss about some results of the Omega Key project. So the Omega Key project collaboration between LCO and several institutions in the world. Me, I'm Etienne Bachelet. I'm currently a postdoc at the Institut d'Astrophysique of Paris. So we speak a lot about black hole during this session, during this meeting actually, but actually microlensing is also sensitive to exoplanets. And here I display the planet population from the NASA Exoplanet Archive. Here on left you can see the mass of planet versus the distance to the host star normalized to the snow line, and we can see that microlensing is actually complementary to transit and radial velocity, in the sense that this technique is more sensitive to planets that are in or beyond the snow line, while the transit and radial velocity methods are more sensitive to hot planets. On right, I display the population of exoplanet in the Milky Way representation. And we can see again that microlensing is sensitive to a type of planet very difficult to observe for the other techniques, in the sense that microlensing is sensitive to planets at several kiloparsec from Earth. And this is because we don't need to measure the light coming from the lens itself to observe the planetary system. And so microlensing has a potential to detect planets in the entire Milky Way, which is very unique. Here I display an example of an interesting system, which is MOA 2010-477. It's an event I published during my PhD. And you can see the light curve on left is due to Jupiter mass planet around, let's say, a body of 0.5 solar mass. And I say body because at the time we didn't know the exact nature of the host. But Josh Blackman et al., they conduct Keck follow-up observation, and they didn't see any flux coming from the lens itself. So they conclude that actually the host is a white dwarf. So again, because we don't need to measure the flux coming from the lens, we are sensitive to objects very peculiar. And in fact, this is the first detection of a planet around a white dwarf. Of course, microlensing is also sensitive to black holes. Here is studied by Łukasz, because black hole produce event of long time scale with small parallax. If we are able to monitor this event for a long time, then we can obtain a measurement of their mass. So I will not go too much in detail, since this subject have been talked a lot already. And here is the work by Kailash Sahu, recently published, where they combine the photometry and astrometry from HST to obtain a direct measurement of the first isolated mass black hole. So microlensing have a very strong potential to detect interesting astrophysical objects. And actually, there is a new potential for microlensing, which are the development of all-sky surveys, such as Gaia or ZTF, Assassin, and in future LST or Black Gem, for example. So these missions are terrific, and they detect many transients every night that need classification and follow-up. And here I display the number of epochs observed at the first year of ZTF, and we can see that in maximum ZTF observe about a few points per week, which is not enough for our microlensing science, because, for example, a planetary anomaly duration is about maximum of 1 or 2 days. So all of this mission have a very good potential to find microlensing candidate in all the sky, but they need follow-up. And here is a display of the potential of LSST by Syed Dijan et al. I display in latitude versus longitude, galactic longitude, the number of events per square degree per year that LSST should be able to detect. And we see that LSST will discover thousands of microlens every year in the galactic plane. But again, with relatively low cadence, I'm going to deserve a follow-up. So for this purpose, we developed the Omega Key project, which intend to ensure dense photometric and spectroscopic follow-up of microlensing candidates. It's a collaboration between LCO and several institutions around the world. And it started in 2020 and will finish next year. And our strategy is basically to conduct a regular follow-up in photometry in 2 bands, basically SD, SIS-I, and G, with a daily cadence for ongoing event. And as soon as an event becomes sensitive to planet, we trigger a priority mode, which is a 30-minute cadence for the next 3 days. In case we have an anomaly ongoing, we can trigger intensive follow-up. We also plan to have a spectroscopy for a lot of events, especially those in the disk where the distance of the source is hard to estimate. Depending on the brightness, we can trigger Floyd's low resolution spectra or high-res N-res spectra. All this observing strategy is implemented in the microlensing observing platform, which is a TOM toolkit database that Rachel described to you yesterday. MOP realize all of the steps automatically, and its first task is to collect the microlensing candidate for the different source of survey, such as Algol or Gaia, etc. Then all of events are fits. We can take advantage of the AWS architecture to fit massively in parallel. And as soon as the fits is done, we can trigger extra follow-up on the LCO network as needed. And then the photometry is done in real time using our new PyDNDA pipeline. And then the system enter a loop, since new data points can can change the model and then modify the priority of the event. So here is a display of all the events collected by the MOP database. We can clearly see that a lot of them are centralized in the galactic bulge. And this is due to the microlensing survey more. And in coming years, it will be Algol as well. We have a couple of events in the Malaysian cloud, but we have hundreds of events located in the galactic disk. So here's a summary. We have this distribution of events. We monitor more than 1,500 of them in photometry, and we collect more than 100 spectra. From all of these events, we classify 62 of them as events of interest. They are binary or planetary, and they show interesting features, could be long duration, etc. And here I'm going to discuss some of them. The first one is Gaia 20 buff, which is one of the first one we collected, and we can see that the Omega project actually observe a plateau around the peak. And in fact, this plateau is due to a binary lens. Modeling conduct leads to several models. Actually, we found 6 models that are possible with a mass ratio leading to a binary star or a planetary mass range for the resonant models. So these models are more or less degenerate in a sense. They are almost equally good in terms of chi-square. The best one is close minus, but the difference in chi-square is only about 40, which is quite small. But here I display all of these models trajectory. So in left, you see in XY coordinates the trajectory of the source in blue and the caustics in red. And in fact, the different geometry and trajectory, while they can lead to a similar light curve, they produce a different astrometric shift, as we discussed a lot during this meeting. This is what is displayed in the center and the right. This is the astrometric shift for all of this model in declination and right ascension. And actually, when the time series from Gaia will be available, it will be helpful to use this data to distinguish between this model, because all of this model produce different astrometric signals. Here is another event, Gaia 21 DNC, which has been detected at a very large latitude, minus 19. And there is an anomaly on the rising part of the light curve, as you can see here. And this light curve is actually due to a planet with a mass ratio of 10 to the minus 3. Currently, there is 2 models degenerate that lead to quite similar planet mass, however, which is 1.1 mass of Jupiter. And so it's a very interesting event. The degenerescence between the model is due to a degeneracy in the source distance that we are currently working on. And here I wanted to display a very recent result that happened last week, which is MOA 22462, and omega trigger very dense follow-up of the peak, and we catch all of these anomaly features. That is well explained by a planetary model again. So today I display only planetary events, since we already discussed a lot about black hole. And to conclude, I will say that more studies are on the way. See, for example, the talk by Paolo Rota and Katarzyna. We observed a lot of events, so if you are interested in an analysis, please contact us. We might have data that can help you. And we are actually preparing for the next key project call in 2023. For the launch of LSST in particular. So I will stop here and take any questions. Thanks.
Thank you, Etienne. Are there any questions? Questions on Zoom?
Nothing on Zoom, but I can make a comment.
Here.
Hi, Etienne. This is Łukasz here. I just wanted to comment on the very nice collaboration we have with the Omega collaboration, and many of us are involved, and especially that the MOP, we've been developing our TOMs in parallel with Etienne, and you see some features of MOP are actually not present in our black hole TOM. So we should definitely sit together someday and improve our TOM, and then also make our TOMs speak to each other, right? Especially in terms of exchange events. So this is a work for us to do.
Yes, so I think this is something we discussed for a long time, never have time to implement. But from what Rachel said yesterday, it seems the softy of LCO codes that, so it should be pretty straightforward to do now. So that will be great.
Yeah, okay. So I put it on the action list.
Okay. Okay.
May I have some? Well, question or? Okay, thank you. Hi, Etienne, that's Pawel. I have a question about the spectra collected in Omega. You have mentioned it, more than 100 spectroscopic data. Which kind of instrument do you mean?
Oh, it's fluids. Most of them are fluids, maybe one or two foreign rays, but most of them are fluids.
Okay. So you have mentioned only Omega instruments.
Sorry?
You have mentioned it only about the Omega instruments like fluids from LCO.
We don't have Omega instrument.
I mean, in the instruments used in Omega project. Like,
yes, it's fluids mainly. So the idea of the spectroscopy is to help for the source distance, but the main goal is really to distinguish, contaminant.
Yes. Okay. Thanks.
Are there no more questions? Okay, thank you very much again. Our next speaker, Maskoliunas from Tel Aviv University, who will present the Aspired toolkit.
Hello. Can you hear me?
Yes.
Thank you. Let me share my slides. This one. This one. Okay. Can you see it fine?
Yes, we see your slides.
Okay, thank you. And the cursor, the mouse?
Yes.
Yep, thank you. Right, good morning, or good afternoon or evening if you're in a different time zone. I'm Marco. I'm currently working in Tel Aviv University. Thank you for giving me this chance to talk to you again for the fourth time about the Aspired toolkit. Although some of you may be new, so hopefully you will take something else from this presentation. So the Aspired is a spectral data reduction toolkit. So as I name it as a toolkit as opposed to a pipeline, is because it is offering you a lot of the functions to do the data reduction, but it is not a black box for you to reduce your spectra. This project started back in 2019, and thanks to all these people here, and also many others that are not named here, that have made this project possible and have survived the last 3.5 years. Today I will talk about why I started working on this project, and some example on the data reduction with the fluids spectrograph with the LCO, and very briefly touching on the software development process and the current status. So this project was first started as a joint development of a portable instrument and pipeline, and the instrument is now called the Spread, is mounted on the Liverpool telescope, and there's a clone, but not exactly a clone, but a very similar design instrument is mounted on the OHB 1.8789 meter telescope, and another one in the SAAO on the CD telescope. But then for the pipeline part, it started off as a groundwork of this Aspired project, but it had evolved a little bit and ended up not being a pipeline, but as a toolkit nowadays. And it was originally funded by the former Unicorn, before it became the current RadioNet pilot, and then it moved through different grants, and I will be looking for money very soon. So if you know about any opportunity, I would be interested to know about. So this project the main drive of this project was because IRAV is no longer officially supported, even though it is currently supported by this community. Their update is very sparse, and there isn't really a help desk to solve any of the problems. And next, the target for the joint instrument and pipeline project was to aim at some relatively low-cost running telescope or observatories. So building a pipeline actually takes a long time and a lot of staff effort, and that would take up a lot of the budget of an observatory. And because of the modern technology that we are moving on to the Internet of Things era, we were trying to adopt some of the newer technology to allow some cross-platform deployment and interactivity, perhaps on the web-based manner. And finally, as we speak right now, the AstroPi support for the spectral data reduction is still very minimal. SpecReduce of the AstroPi just released a version 1.2 yesterday, I think, or the day before, and it is still only supporting spectral tracing and spectral extraction and nothing else in the spectral reduction process that are necessary to get any science done. So the Aspire itself is divided into two main parts. Well, actually just one main part and a very tiny part of this image data reduction module, because our main drive is to allow users to do spectral data reduction, but not the image reduction. So what we are providing here for the dark bias subtraction and flat fielding stacking, they are absolute minimal, and it should be sufficient for very basic instrument only, but not for something more complex, as we will see in the LCO example in a bit. And in terms of the spectral data reduction, then the module divide the processes into roughly these 7 steps, from identifying the spectrum on an image to correcting the curvature of the spectrum into a straight line, and then extract it into a 1D spectrum, and then apply the corrections, calibrations, and higher order corrections. So say take the LCO Floyd pipeline as a spectra, and then as an example, it is a cross-dispersed low-resolution spectrograph. There are a pair of them mounted on 2 different telescopes, the FTN and FTS. And the tricky part of this spectral image is that the red and the blue at the top spectra are simultaneously exposed onto the same image, and they are both curved, and the curvature are different, and they're physically, the XY limits of the spectra are also different on the same image. So what we have to do is to first mask the 2 spectra before we can proceed onto the data reduction. And this is an example about how this is not a simple setup, that our image reduction module is not capable of handling it, but we have to do some pre-processing before we can proceed onto the data, spectral data reduction. So now I'm only taking the red part of the spectrum, the bottom bit, this one, as an example. So all the images, this next 7 or 8 slices, I'm showing you the output image directly from the aspired output, the default one without any tinkering. So on the right here, what you're seeing is the red arm spectrum, and the black line is where the spectrum is being found. So the dispersion direction is where the spectrum is dispersed with the wavelength coordinates, and the vertical direction is the spatial coordinates. And since this spectrum is rotated and the dispersion and spatial axes are only locally orthogonal, but it is not orthogonal when we are viewing it in the detector coordinate system. We have to perform a form of rectification to straighten this spectrum before we can reduce the data further. And so what you're seeing here is after the rectification, on the top is the spectrum, and at the bottom is simultaneously applied to the arc lamp image as well, because that is necessary for us to do the wavelength calibration. And what you're seeing at the top here is just some internal reflection. And also you see this curved line here and another one up here. This is the original edge of the detector and got shifted that way. So after we know where the spectrum is, we can extract them and turn it from a 2D spectrum into a 1D. And so on the top here, the black box is showing you the area where the extraction is taking place, and the red rectangles are showing you where the sky background is taken from. And at the bottom is the sky spectrum, which is dominating the flux as for most of the faint sources. And the blue line here, the extracted signal, and the gray line here is the signal to noise. And so I'm also providing three forms of extraction. One is the top hat, which is a direct sum of everything within the black box subtracted by the weighted sum of the sky that would match up the pixel numbers. And two other forms of optimal extraction. One is by Horn 1986, and the other one is by Marsh 1989. And after we know we have the spectrum, we want to extract the arc spectrum with the known element, with the known with lines at known wavelength positions at the same place on the detector position, in order to get this arc spectrum, where we can have to identify the peaks so that we can find a solution or a mapping from the detected pixel value to the spectral to the wavelength of the spectrum. And this is the output for using the concurrent development software called NaCo that does the magic of wavelength calibration. So at the top here is showing you all the identified lines and the fitted lines. The middle is the residual and the RMS in the two black dashed line, and the bottom is the pixel to wavelength polynomial. And I'm not going to spend too much time on this one, but if you're interested in the wavelength calibration process, please contact me. I can talk to the I can forward you to the PI of the project. And then once we have the wavelength, then we can compare our spectrum to the golden standard from literature so that we can actually apply the flux calibration where the spectrum we extracted just now was in the unit of electron counts per second. But what we have to do science with is the flux value itself. So we have to take a standard and then to get a sensitivity curve which is in the unit of flux per electron counts. in order to know how the detector is behaving at different wavelengths, at different position of the detector. And after getting all these, then we can put all the calibrations together, and then that's how we get the wavelength and flux calibrated spectrum. And after we have done this for both the red and blue part of the spectrum, then we can combine them together to get the entire spectrum from 3,700 to 10,000 angstrom. So I think I will skip this one. So basically everything is hosted on GitHub, and most things are automated, and the plots are powered by Plotly. And so in the end, I will leave a page with all the links. And currently we are at this version, and I'm hoping to release the next iteration by the end of the year. And currently is mostly waiting on the wavelength calibration. And in terms of the Floyd reduction, there is actually an unofficial pipeline that I'm building, and it is at a very late stage of the early development phase. So what that means is it is not quite entirely working yet outside of my computer, but it is close to that stage. And all you need is TNS and LCO login details and a YAML file, then it should be going by the time I get it published. And currently, it is used as a quick look data reduction pipeline on the Observatory, the Hawk performs 1.93 meter telescope mystery instrument, and it is unofficially tested with this list of instruments. And on the right here, I'm comparing the blue line for the aspired reduction and the green line from the VLT4s using a Starlink-based reduction, and the red spectra are all reduced with IRAF-based reduction for the Floyds, for the Liverpool telescope spread, and the Gemini GMOS in the long slit mode. And just a few more examples showing a simultaneous extraction of two stars incidented simultaneously on the long slit, and some example low signal to noise extraction and extraction with many absorption lines. And so I will leave this page here, and I would be happy to take any questions. Thank you.
Thank you very much, Marco. It's great to see those developments in publicly available software. So are there any questions in the room, Milena?
I don't know. Thank you. Can you hear me? Yeah, I guess. So thank you, Marco. That's a great job. And I believe all of the people working on the spectral reduction are really appreciating what you are doing. So congratulations. As far as I understand, the pipeline is dedicated, well, the Aspired is dedicated to data reduction of long slit spectra. Are you planning to somehow, if there are options for also financial support of the projects, to extend it for shell spectrographs?
Yes, so I get this question a lot, and I think with the current landscape of the many efforts in dealing with spectral data reduction, the answer should be no, because if you look into the Zoom chat, class has actually mentioned one pipeline that is really good at handling the shell spectrograph, but it is very specialized. It is, I actually try it. It is really difficult to get it to reduce a normal long slit spectrum. So, but if you want to do that, PyReduce is doing an amazing job in reducing shell spectrograph, and that is really, I would be a few years behind in order to even compare or compete with the PyReduce spectrum. So currently, I really do not have any plan on the shell spectrograph.
more questions in the Zoom, maybe? Oh, Łukasz has a question. Here.
Yeah, so there is this question on Zoom, Mark already noticed, but could you, so from class, it's a very nice toolkit. Can you comment on how it compares to other toolkits like Pawel, fire reduce? You already said that the shells are included there, but how the performance compares for long slit observations?
So for Pyrogeos, I can't really compare it because yeah, it is a little bit different, and also the Pyrogeos, they have their new way of doing their optimal extraction as well. So what we are comparing are actually down to the algorithmic level rather than what the software that is making use of those algorithms. And for Pawel, I am actually planning to try using it again and see, but I haven't touched it in at least 2 years. And from my experience before, Pawel was a complete black box that there are not many options to modify the code to suit your own task, your own instruments, but instead you have to contact them and then they will try to build something for you. In terms of the quality, I have heard from the LCO that Pawel, when using their most accurate mode, it is very good, and it is completely useless in terms of the data retention when it handles any form of transformation or resampling, but it is extremely slow. But when it is using the normal mode, then I would say the quality should be comparable. But it is the extraction quality is always down to how many bugs we have in adopting the optimal extraction algorithm that is published, written in paper, not written in code. And it's always a little bit of a problem here with plus or minus 1 or 0, some here and there, and yeah.
I think that were all the questions, all right? So thank you once again, Marco. Thank you to all the speakers in this session. Thank you everyone for being on time. So now we're having a coffee break and we meet again here at 11:10. jest
Mają.
pytaniami.
Na pytania mają tam.
Dobra. To co zapowiem tym, już będziemy chyba sobie podawać.
No. No, sprawdzę, co tam jest. O kurde, szybkie to.
Teraz widać twój brzuch.
Generalnie zawsze
Tu
go widać.
będziesz stać. O, teraz wyglądasz dobrze.
Generalnie zawsze widać mój brzuch.
Więc generalnie mniej więcej odtąd, gdzie stoisz, może trochę bliżej do tego.
Jak tam uważasz, ile mam? 15 minut jest? No to
Zaczyna jest 20 minut z pytaniami.
15 z pytaniami. Co możesz pokazać? Końcówka tych 15 czy jaki masz tam rzeczy? Myślę, że się wyrobi w 15 minut. To pokaż, to pokaż. Dobra.
Już, Zasiu, no to zaczynamy.
Hello everyone. We have a small change in the schedule. So the first talk will be by Pawel Zielinski from the Nicolaus Copernicus University in Torun, and he will explain to us his distrust for Gaia parallaxes in Microlensing events.
That's right. Thank you very much, Maya. Sorry, Zofia. But yeah, I would like to thank Maya as well. I'm Paweł Zielinski, and I'm gonna to show you a few slides about the problems with Gaia parallaxes, especially for microlensing events. So in general, this will be about spectroscopic classification of Gaia alerts. And the title of my talk is Why Can't We Trust the Gaia Parallaxes for Microlensing Events? Let's start with big thanks to all of the observers, support astronomers, data deliverers. Thanks to them, we have a lot of data gathered, spectroscopic data from many different facilities, telescopes, even 10-meter class telescopes. So this is really great job. And based on this data, we are able to determine the parameters as well as distances to our targets. Why do we need spectroscopy? This will be about spectroscopic analysis, but what for we need spectroscopy? I'm working together with Łukasz and his group. So the targets of interest, the microlensing events are our targets of interest. So we need spectroscopy to distinguish the genuine microlensing events from other types of outbursts and variables like big stars, young stellar objects, cataclysmic variables, and etc., etc. So on the right side of this slide, we have Gaia light curves, only with Gaia data points in G-band. And the black dot shows the moment of the alert. So at this time, we are not sure what we are looking at. All of these types of changes in brightness can be caused by microlensing events. And we want to know that we won't lose time, precious observing time, to observe some other variables other than microlensing events. So that's why we need spectroscopy to select a sample of microlensing events for which follow-up, ground-based follow-up photometric monitoring will be continued. And you must know that Gaia alerts are usually not classified. Only 1/3 of them are classified. So the rest, the vast majority of Gaia alerts published in Gaia Science Alerts webpage has unknown status. Of course, together with, if we have spectroscopic data, we can determine the atmospheric parameters, masses, radius, temperatures, surface gravities, line of sight extinction, but also we can get spectroscopic distance based on these parameters. And as you know from previous talks, the distance to the source in microlensing events is essential in solving the microlensing model. This is based on that we can determine the distance and mass to the lens. But we have Gaia, and there are Gaia parallaxes. So why do we need to bother about spectroscopy? Well, Gaia is great and delivers a lot of very precise parameters, proper motions, parallaxes, coordinates, also photometric measurements. But for some objects, for example, for microlensing events, the Gaia measurements, Gaia parallaxes can be wrong due to astrometric microlensing, which means that the centroid shift motions is visible, is affected during the event by this, the measurements of this centroid shift is affected during the event. So here we have a simulation done by Chris Rybicki, showing the ratio of the distances between the source and the lens on the x-axis. On the y-axis, we have the ratio of the fluxes between source and lens. And red colors indicate the place, the space where Gaia underestimates the distances of the source and claims less than 30% of the real value, which means that, only that the Gaia is wrong in this, actually in this place for blended sources and light. This is for blending light objects. So we cannot trust it in these measurements. We are pretty sure that it can be affected from some reasons. For the most typical distances in the Milky Way, so for example, when we have sources at 8 kiloparsecs in the bulge and the lens at 4, more or less, kiloparsecs, Gaia distances give 80% of real values, and this is the dotted vertical line. So even if the source is 10 times brighter than the lens, like here, we have 80% of the real value of the distance. So I have mentioned that many observers and many facilities were used in our study, and we used the telescopes included in ORP, Opticon RadioNet pilot follow-up network. This is a network of the volunteering observers. So mostly photometric observations were done, but also spectroscopy is possible thanks to the observing time awarded or thanks or just on request by sending simple email with some asking about the spectroscopic data. So these are the examples of low resolution spectra, the examples of telescopes we use to get low resolution spectra. So very often we used SALT, RSS, Liverpool telescopes with Spratt instrument, both Geminis with GMOS at north and south, and also Shamaki Astrophysical Observatory telescope, 2-meter telescope in Azerbaijan for obtaining high resolution spectra. We used usually VLTI with X-shooter spectrograph. It's a great instrument with very nice sensitivity. SALT with high resolution spectrograph, and also we use twice large binocular telescope with great Pepsi spectrograph with this beautiful resolution power, 250,000 at maximum. So at the moment we know more than 500 microlensing event candidates detected by Gaia, and we obtained spectra for 190, both low and high resolution. For 55 targets, we get high resolution spectra, and for them, we are able to determine the parameters with sufficient precision, let's say. So here we have the distribution of these Microlensing given candidates on the sky and the histogram distribution of the brightness. So usually we have targets around 15, 16 magnitude. And actually this is the 16, 17 magnitude, let's say, for each shooter. This is the magnitude limit to get a high resolution spectrum. For the rest, we got only low-res data. These are the examples of low-resolution data. So here we have Shamaki telescope and camera and spectrograph and spectrum, Sprat spectrograph and GMOS N North from Gemini. So based on that classification spectra, we classify our targets onto two groups. Normal stars, which means these are stars with only absorption lines, with no clear emissions. So these are potentially microlensing candidates. And the second group is non-ULENS, non-normal stars. These are variables with emission lines and emission features, prominent lines in emission, like P stars, young stellar objects, etc. So after that, we concentrate on microlensing candidates, and for them, mostly, we obtain high-resolution data to do absorption line analysis. So we would like to know the temperature, surface gravity, and metallicity, and together with some isochrones, evolutionary tracks, and empirical calibrations, relations, we are able to obtain radius, mass, absolute magnitude, and also the template matching, which is visible on the left plot, give us the line of sight extinction in the direction to the source. Here you have the two spectra from each shooter from July and November 2019 for one of our targets, and you can see the solid line, which is a model with extinction, compared to the dotted lines, which are models without extinction. So it's based on that we can determine the extinction to the direction of the source. And on the right side, we have a comparison between observed spectrum, okay, from VLTI, blue one, and overplotted on that is synthetic spectrum, theoretical spectrum for specific parameters. So thanks to that, we can obtain the spectroscopic distance. So this is an individual determination of the distance. And now two examples. First one is nice and easy because this is well-known Gaia 19 BLD, already published in this year in 3 papers. The first one is about spectroscopy. So this is a giant, late-type giant, K-type giant, metal-rich, with extinction 2.2, and the distance from the spectroscopy is 0.4. The distance from Baylor-Jones determination is almost the same, 0.9. And this is a nice case because it is in agreement, right? Both distances, they are in agreement. The Gaia parallax is, uncertainties is quite reasonable, small. And the Ruve parameters, the normalized unit weight error, is around 1, which means that there is no problem with astrometric measurements done by Gaia. But there is another case, Gaia 18 AJZ. And for that case, for this bright giant of late-time stars, metal poor, we got 11.5 kiloparsecs, while Gaia DR3 data from paper by Baylor-Jones is completely, from another side of this range of distances, and distances obtained in the second work of Baylor-Jones based on geometric and photogeometric parameters is also several kiloparsecs away from our measurement. So this is problematic actually case, because it shows that we cannot trust Gaia parallaxes, probably due to astrometric microlensing. For this target, Ruve parameter is above the limit of tolerance, which is 1.4, which means that there were some problems in astrometric signal during the event, and the Gaia parallax was determined with sufficiently high precision. And the last slide, with the plots, with the comparison between spectroscopic and Gaia EDR3 geometric and photogeometric distances, we see where is Gaia 18 AJZ, the most problematic target in our sample, and we have several other examples which were discussed yesterday and the day before and today. So, for example, here is Gaia 20 FNR, which is in very nice agreement. What we see is that the spectroscopic distances are determined with much better precision than the parallaxes, than the distances measured from Gaia. So, summarizing everything, the spectroscopy is crucial when we want to select microlensing events for further monitoring. 27% of our targets were classified as such events. The rest are variable stars. So this detailed spectroscopic analysis is possible. For the first time for these targets, we can get stellar parameters and distances. And of course, spectroscopy gives us a chance to independently estimate the distance that can be compared with other measurements. So, like, for example, Gaia parallaxes. So, take-home message is that please be careful when using Gaia parallaxes. For the vast majority of such measurements, Gaia is perfect instrument, is perfect mission. But you must be aware that there are some problems with some specific targets like microlensing events. That's all. Thank you.
Thank you very much, Pawel. Are there any questions?
There is one on Zoom.
Okay.
So the question from Etienne is the agreement between spectroscopy and Gaia distance improve with the increasing of the ratio F source to F blend?
Could you read that again?
Maybe you can ask Etienne to.
Yeah, I'm going back to.
Yes, so do you hear me?
Yes, yes.
Yeah, so the question is, you show, for example, an agreement for BLD, where I believe the blend ratio was pretty low. So I would have seen that the agreement between the two methods increase if the ratio of the blend light decrease. Do you know that for other events?
Actually, I haven't checked that carefully, so I cannot say nothing about some simple statistics. How many events with low blend is, what was determined, the distance for them was determined with better precision.
So, for example, in your plot, you could color coded the points with the blend ratios that will be informative, I believe.
Yes, like here, yeah.
Okay, any more questions? Again, Zoom.
So Marco Lam is asking, do you think there is a hidden non-interacting white dwarf in binary with the red giant?
Well, it's a good question. When we analyze the spectra of our events, actually we assume that there is, we do the spectroscopy at high magnification, usually. So which means that we see the light from the source. And we assume that there is, one source because the resolution is not enough to distinguish between some binary source, or even binary lens is even worse scenario. But of course, they can affect some light from this blending background stars even, or blending line, some sources around this our events can affect this spectra, and of course we can have some blends visible in the lines. But with this resolution, it shouldn't be a problem. I think that we need to have a resolution more than 50,000 maybe. So only for the brightest stars in our sample, it could be visible, but not for the rest, I guess.
Okay.
Okay. Any more questions? Actually, I'd like to ask, because I was impressed with how the distances differed for the AJZ events. Were you able to identify, was it because of it, like, was it the luminous lens, or was it just the crowding around the source, or was it astrometric lensing? Can you distinguish between the scenarios and determine which effect is dominating there?
Actually, not at this moment, because after Gaia DR4 release, we will have epoch astrometry for all of these targets. So then we can check the time series, astrometric time series for this event, and we can rule out some periods with high scatter in these measurements, for example, or I don't know. We can say more about the period of time when the astrometric lensing was possible, could affect this measurement. That's why, for example, the Ruve parameter or other astrometric flux and parameters are so high for this event. But the problems with that event is also because it's really faint. It's 18 magnitude or even 19 magnitude event. So yeah, Cornell confirms that. So yeah. So this is also a problem even for Gaia, because the parallax uncertainty is quite high for this target.
Great, thank you. Thank you again, Pawel, for your talk. And our next speaker will be Marius Maskoliunas from Institute of Theoretical Physics and Astronomy at the Vilnius University, who will present a comprehensive way of determining distances to source stars.
Thank you. How to use this device?
This is back, this is forward, there's no later.
Yeah, it is lighter. Yeah,
Middle,
in the middle. Yeah.
Move. Very fast. Wait. Okay, so
Use the microphone. No.
thank you. Actually, my talk, my presentation today will be very similar to that Pawel started, as well of discuss about to determine the distance to the source star, because actually the distance is one of the most difficult issue in astronomy, especially when we're talking about the object located and quite long distances. So, and okay, so typically in microlensing event, we see the source star, and some between the source star and us observer, some object, invisible object, but with mass. And so we can detect this or calculate or put to the model to calculate the mass, only knowing location of this our source star. So that it is essential for our for modeling for our and I confirm the same idea despite, let's say, Gaia accuracy. Perfect instrument, but in our case, probably for statistic to talk for the statistic is a little bit too early, but probably will be need to spectroscopic parallax to use in the future. So my I put attention to this presentation, and I put my attention into this 4 targets. Not all, 3 of them are published, and the last one, it is work on progress. It is, and actually for this target, it is determined the distance using the many different ways. So, okay, so let's go to the distance determination. In principle, it is 2 most widely used methods. One, it is parallax method, that it is all for you, it is known, yes. And other, it is spectroscopic parallax. Actually, it is based on location of a star somewhere on the, where is its location on the HR diagram. So if we know the absolute magnitude, if we know apparent magnitude, extinction as well, so we can calculate the distance to this our source star. Now, when I started many years, my interest in astronomy, so at that time was just published Hipparcos data. So precision was until 100%. So now, of course, for Gaia, few kiloparsecs we can talk. So of course, it is going into the development. But both methods has its advantages, would say, and disadvantage. So actually, Pawel already mentioned, I prefer to use Bachelet-Jones' latest catalog, where it is the source for 1.47 billion stars. And actually, in this catalog, he presents very interesting ideas. So, provides geometric distance and photogeometric distance. So, in case of a geometric distance, it is, in principle, it is recalculated distance to the source using parallax. So actually, parallax geometric distances. So additionally, this into calculating this distance, additionally included the color of a star, and apparent magnitude. So this is additionally two parameters. If we're talking about parallax, for example, if we take the Gaia parallax, it's simply we want to calculate from the distance to the source. We need not to forget that parallax errors, they follow distribution errors. Distribution is by Gaussian. Yes. But if we translate these errors to the real distance, we see that it is not Gaussian distribution. It is unsymmetric. So it is untypical to the longer. So if we use only parallax, so it should be so. Actually, most probable distance is it is a little bit on more than exactly if we take only parallax measurements. So, okay, now let's move to spectral parallax method. So actually, idea, it is based on this simple equation. And actually, this looks quite simple because it's apparent magnitude, it is absolute magnitude, and it's extinction value. But here it is actually in every one of this, it is some hidden issues, let's say like this. And about every one of these issues, I describe. If you look into this one, apparent magnitude, yes. So now we know that it is a telescope measuring, a good telescope measuring, it is in millimagnitude level. So coming LSST telescope will be on millimagnitude magnitude. Errors will be magnitude. It belongs, of course, with source. So it is, but the most issue, but we do not nothing about duplicity and variability of this. So it is can be some stars itself are variable. For example, young stellar objects were variable. Some of the red giant stars it is also variable. So it is now. So, but with this variability of if a source was single, we can check with imaging imaging, and here it is on the two objects that it is we're taking with, on the left side it is with Gemini 8 meters telescope with adaptive optic, and other example for Gaia 1680. So no, on this images, no signs that it is that some object can be double or something, because if it doubles, so typically on double stars, sometimes on the images will look like ellipse or something. So here, so one of the way to solve this problem, duplicity. Okay, another way, it is actually if you have good spectroscopy. So it is example for Gaia 19 DKI follow-up observation spectroscopy. So spectra also provide for us, it is possible if it is close binaries or something where I have they show on the spectra. So actually, I'm talking about Gaia 19 DKI, since this is not published yet data. So actually, it is not shows that it is this object probably this is single and okay, and now it is, if we're talking about absolute magnitude, it needs to remind that actually this absolute magnitude is calibrated during our observations from the HR diagram, where it is typically some middle values. When our source star is the main sequence star, yes? So actually this scattering these points or wideness of this main sequence star, yes? It is some has some wideness, and of course we can predict that maybe just we only take attention to this HR diagram and assume that absolute magnitude it is on some level, but it is absolute magnitude can vary for the main sequence, and even for the GNs, for example. So some GNs, if you look to the HR diagram, so you see that it is the scattered, it is like small cloud that is like located in this HR diagram. So it is even more can be absolute magnitude. And third parameter that it was on this equation, yes, it was extinction. Now I would like to remind that this equation that it is we can apply for any photometry system. So it is of course started from the UBV system, and now it doesn't matter. We can use it into mass and other surveys. But for use other surveys, we need to do intrinsic position. And it is how the star looks in this example, color diagram, if it is not redundant. So here it is again, the Gaia. So if you put that to mass data, yeah, so now this target 19 DK, it is here, this red point. Here it is, we say, photometry say that it is unredundant, the star. So actually, if we calculate extinction, so this star appears in this position if it will be without extinction. So, and here it is sequence for the GN star, different spectral types. So actually, if you look to this, it is the star located in agreement, let's say. Other than hidden parameters, it is if you're talking about extinction. Yes, it is this typically R parameter if you use UBV. Here it is in two-mass system, it is 0.67. In UBV, it is typically about 3.15, but it depends in which direction they are. So it is in UBV system, like most famous, but yes, it is 3.15. But we know that, for example, extinction value in Cygnus 3, yes, it is 2.8, 2.9. In some directions, even it is even 4 or 5. So it is as well this parameter. And if you calculate for extinction from different photometer types, so we know that extinction affect the stronger affection it is on short wavelengths, and for infrared it is low affected. Yes. So if it is calculated from a different, like from one stars or something, the data, yes, and to two mass, and you see that something is disagreement because between AV and AKS it is 843. Oh, it's this value. Actually, this value here it is in agreement determined by Percy telescope. So we determine at 1.7, so 1.66. So actually, this, if you want to use this spectroscopic parallax. So we know our way to put careful attention to these three parameters, what it is in this equation. And okay, so now this I mentioned in the beginning of my presentation. I mentioned that it is preliminary result. It is based already on published Gaia alert, Gaia lensing factors. Okay, so when it is a summary. So that it is in our papers accepted distance. Yes, and here. So here it is with two columns. It is two columns. It is Bachelet-Jones photogeometric, geometric. It is the parallax from the Gaia. Yes, and it is the Gaia DR3. Right? Yesterday we took this. So actually in this example, we see that only Gaia 19 BLD, we accepted in the different methods, 8.4 kiloparsec. Yes. So in reality, Bachelet-Jones provides, let's say, in agreement with distance. So if you look to CBF, Gaia 18 CBF, yes. So if it negative parallax, so it is no, at least we know that it is the distance object, negative parallax, yes. But in reality, we accepted that in distance it is 18.2 kiloparsecs. So actually, I understand that it is only for examples. So for examples, for statistics, it is really not enough, yes? But probably in our future, when will be data from the surveys like LSST and other, or NC Roman telescope, probably we will be, for distance determination to the source star, we will need to use this spectroscopic parallax, not geometric parallax, not trigonometric parallax. No, that's my summary. Oh. And okay, I would like to acknowledge that it is this job, its work is made due to the research project Polish-Lithuania Black Hole Grant and supported by the following grants from the Polish National Science Center grant and by a research council of Lithuania. So unfortunately, project going to the end. It is finished this year, and it is my Molėtų Observatory. I am not alone. It is our group, our team, but it is involved in this project. And thank you for your attention and waiting for questions.
Any questions in the Zoom?
No.
Questions from the audience? No? Okay, let's thank Marius once again. And we are now switching to virtual space, and the next speaker will be Piotr Kolanderski from the Nicolaus Copernicus University in Torun, who will speak about quantum communication with a satellite link. Hello? The next speaker will be Piotr Kolanderski. Are you there?
I think he didn't notice the program.
Oh, he probably didn't notice the switch. Okay, so
Well, he's there.
let's have our next in-person speaker, who will be, according to the schedule, Milena Ratajczak from Warsaw University Astronomical Observatory, who will present spectroscopic follow-up of eccentric binaries.
So good afternoon already, right, everyone? Hello to all the people on Zoom and cyberspace. And I will be talking about stars and actually about binary stars, especially those in eccentric systems, and the spectroscopic follow-up of them. So why are we actually talking about this kind of stars and this kind of observations at this kind of workshop? Is described at this very first animation that shows you that for a eccentric system, both in terms of light curve and radial velocity curve, Sometimes it happens not much, and at some moment in a phase or in a time domain, there are some changes happening, and the changes are related to,
Try next.
Yeah. So you see the changes in light curve, they are here, and now I have to do it again, like this, okay. And in the radial velocity, they happen in the same moment. So in the time when there is a periastron passage of two components. So the changes in the light curves may be related to eclipses or to some tidal deformation of a stars in a system, and radial velocity changes are related to the fact that stars come close to each other, they speed up, so the radial velocity values are going up and down, as you can see at the plot, and we see these changes. And then, for example, for some months or even years, there's nothing really happening interesting in both radial velocity and light curves. So eccentric binaries are unique tools for working on gravitational effects and also orbital dynamics. And there are two subgroups of this kind of systems that are extremely important, and those are obviously eclipsing binaries, so eccentric binaries that are also eclipsing, and the type of stars that we call heartbeat stars. So these are the stars that actually undergo tidal interaction when they're close to each other, when both components come to each other. During my talk, I will just show you two examples of this kind of systems that are quite nice laboratories for testing these theories. And I hope to convince you that binary stars are not boring, as it was said previously. So the first star, N-Scorpii. N-Scorpii is a very bright system. It's fourth magnitude star, so it's something that is kind of unique because not many people work on very bright stars. And actually, it turns out that some of they're still kind of mysterious. And on the left-hand side, you see the plot, the light curve that was taken from the Bright constellation. So Bright is a constellation of 5 nanosatellites that were observing bright stars in terms of checking their, let's say, pulsations, things, and their variability in general. And as you can see, we see that two eclipses of the star, and fourth magnitude star was not known as an eclipsing binary since then. It was like a few years ago. And actually, you see the time in between two eclipses is only 3.5 days. And object was observed by Bright for half a year, and we couldn't see more of the eclipses. So we assume that actually the eccentricity of the system is pretty high because there is nothing happening for half a year for that system. And we didn't have more observation of eclipses, but actually there is something that comes to as an help that was quite unexpected. And it's a SMEI instrument on Coriolis satellite. And actually, it's an instrument that was working on studying our sun. So basically, the spacecraft itself was about to check coronal mass ejections. So it turns out that this kind of heliophysical physics-related instrument was helpful in studying stars in the background, because as you see from the little image here, there are some dots, bright dots, which are stars. And actually, if you know how to deal with this data, and Przemek is one of the person that knows how to deal with the data from SMEI, you can actually get photometry and brightness measurements of the background stars. And this is the quality of the data is not ideal, but still it's enough to get, for example, the period of this system. And because we saw several eclipses in a data in SMEI, and it turned out that the orbital period is 220 days, so orbital eccentricity is pretty high. So knowing that the eclipses and the periastron passage is coming very soon, we had this campaign. It was before the time BHTOM was created. So actually, we just use our channels to send a request to observe this system. Fourth magnitude system is not difficult to be observed, both in photometric and spectroscopic regime. So we get some alerts and some observations. We also were given, someone was making visual observation for us. So for example, I get a Excel file of data of someone who was actually observing the star by eye. Well, it was not much useful, but I appreciate the effort. So thank you to the observer. We also get some direct alert time on SALT, which was also not easy since fourth magnitude stars observed by 10 meters mirror. It's not an obvious case for some of the tags. but it went through the directorial time. And this is the radial velocity curve of Anscorpi. And as you can see, the changes in radial velocities for both components, because actually during this periastron passage, we could see both components, is pretty huge because we have like more than 300 kilometers per second difference in amplitude of radial velocities. So thanks to that, we could actually disentangle it during the periastron passage because that's a star that is actually early type. So it's not so obvious that we can deal with the data. It's also a rotating star, so it was not so obvious that we could determine both radial velocities in terms of these stars, but it turned out that it was possible. So we get a model of it and characterize the system itself. As you can see, eccentricity 0.93. It's really huge. And two components of around B-type stars somewhere in the main sequence. So that's the main message. So when we put the eccentricity on a eccentricity in period diagram, we see that it's almost a winner. So it holds the second place. It's the red dot here, but the winner is a star that is that plot is related to eclipsing binaries. So only to those stars for which we can get masses quite easily. So not to all of eccentric systems, but those that we know the masses, so which we can characterize pretty well. So the winner is a system eclipsing binary system with low mass components. So we can say that Anscorpi, that is the red dot here, is the most eccentric system among the eclipsing binaries with massive components. So that was quite useful also in our project because the observation of the stars was a part of the project trying to determine which evolutionary models for B-type stars are more precise in terms of location of terminal H main sequence. So as you can see at this, we call it observer's RJ diagram. So basically a radius and a mass plot for stars for which we can get the information about both parameters with a precision better than 3%. And if we put the stars on a plot, so with the violet color, you see that depending on the model, the end of main sequence may differ. And actually what we tried to find in this project was the stars in between the dashed line and the solid line to actually get the information if there is no stars there. So that means that terminal H main sequence ends where the dashed line is, or if basically there are stars, but we haven't observed it there. So as you can see, the more massive star of Anscorpi is actually very close to the thumbs of the dashed line. So it didn't give us an answer in that case, but it's still a very precious point in this project. So with this, I would like to get to the second system. It's a heartbeat star observed by the OGLE project. And heartbeat stars are this kind of stars that became actually very popular after the Kepler data release. So these are the stars for which during the periastron passage, they overcome some tidal interaction that cause stellar deformation. So basically star or both stars are not spherical anymore, and that can cause brightness variation, and that's what happens in this kind of system. So by the beginning of this year, there were around 200 heartbeat stars known, mostly from a Kepler observations and short period and actually low amplitude changes. And when we look at the light curve, which is shown with the black dots and red model here, we see that there is like a big changes in a light curve that this resembles actually the electrocardiogram sign, and that's how the heartbeat star's name is taken from. And also the radial velocity that you see that are notated with the blue dots and blue line in the model, they change a lot during the periastron passage. So the important thing is that the shape of a heartbeat itself, it depends very, very strongly on orbital elements, so on the orbit of binary star itself. So it depends also on the inclination of the system, and the argument of periastron and eccentricity. And the amplitude of the changes and the light curve, they depend on masses of the system and also separation at the periastron. And as you can see at the plots that are shown here, depending on the values of eccentricity, the blue are the eccentricity 0.4, the red are eccentricity 0.6, the shape of the heartbeat itself takes longer or shorter part of the phase, orbital phase. And then it also changes depending on inclination and argument of periastron. And this is super, super important because like we need inclination to know masses, and we have inclination only in the terms of eclipsing binaries. So this is the way that we can actually determine somehow masses for binary systems without knowing without having and detecting eclipses, because these are not eclipsing stars, just eccentric systems. And at the beginning of this year, we published a catalog together with Marcin Verona, the PhD students from our institute, where we found actually 1,000 of such systems, so heartbeat stars. They were analyzed, they were found and analyzed really nicely by Marcin. And actually, you see a full collection of different various numbers in terms of centricity, inclination, argument of periastron, and so on and so on. And one point that one system that made our attention to be focused on it was this Ogle BLG HB6312, which is a red dot at the amplitude and period diagram. That's the diagram that was before publishing our catalog. And as you can see, it's a winner in terms of the period, because the period of this orbital period of the system is 3 years. And actually, it was also very high in terms of amplitude changes. Okay, there's one ASSN very high amplitude system that was published slightly before our catalog. And after publishing our data, the plot looks like this. So this is our point, the blue one here. So the blue are the galactic bulge heartbeat stars. Then the green one are LMC heartbeat stars, and the orange are SMC heartbeat stars. So 1,000 of them. So you see now this amplitude and period diagram is populated much more with this number of heartbeat that were given by the Ogle survey and the hard work of Marcin. That's the system that I was mentioning. So the changes of the brightness, this is just like a zoom on a face, because there is almost nothing happening for 2 years and 11 months. And then within the month, there are some changes, as you can see here. The period 3 years, eccentricity 0.8, that's the more important message from this point. And also, so we started to observe the system spectroscopically and to get radial velocities, although that system is much fainter than the previous one. It's around like a 17th magnitude system, so it was not so easy. But we get some information. So you see radial velocities with quite higher error bars and no secondary detection. So we don't see the secondary in the system. So we see only a primary star. We assume it's a red giant star. But to get more, we started to investigate the system further. So one thing that kept our attention was the changes after the heartbeat phase in terms of seasonal changes. So we have several seasons of that's what Ogle gives us, like 15 years of data for this given system. So we see several seasons. Every color is a different season of the data. And when you look at this part of the plot, so after the heartbeat phase, so you see that in some of the seasons, you see the dip after the heartbeat phase, and in some it's actually flat. So we were wondering what causes the changes after this heartbeat phase, if that could be an eclipse, for eclipse of a secondary star, or maybe the eclipse of some kind of disk or whatever that could be in that system, and we started to investigate it. So there were several questions related to that thing, and one of them is related to eccentricity and period itself. So it's an evolved system with an orbital period of 3 years. Why circulation didn't happen in that system? Why still eccentricity is so high in that system? And also what causes this brightness changes beyond the heartbeat phase? So this just after the heartbeat phase changes. And the third question, which is super, in my opinion, interesting, is what will be the evolutionary scenario, or what was the evolutionary scenario of that system? So we started to work a bit more on that. And something that we have from heartbeat, as I already said, is inclination. And if we have inclination, we can basically get the information about masses, because we know the mass function of that system. So K, semi-amplitude, is known from a radial velocity, orbital period is known, eccentricity is known because of the heartbeat, and also the inclination is is known from the heartbeat phase analysis. So if we have a good estimation of primary star and mass, then we can get actually the mass of a secondary estimation. So that's how the mass function for this system looks like. So for example, if we assume that the primary star has 3 solar masses, then we see that the secondary star is around 1.5 masses. So we have to estimate the mass of the primary component. Spectroscopic analysis came with a help, and we know that the star is around 4,000 kelvins with log G 1.26, which means it is some kind of giant evolved star. We have also a metallicity from it. And if we actually put it on a kill diagram, so log G over log effective temperature, we see that evolutionary tracks for this kind of stars, like evolved stars, are very close to each other. And taking into account the errors of the parameters that we have, we cannot actually say from this evolutionary tracks if the star is 1 solar mass, 3 solar mass, or maybe even 4 solar masses. So this is still an unknown. We started to also play with the Roche-Loeb overflow, and then actually, no matter what masses we take and what radius of the primary star we take, we know that at periastron, the system is very close to Roche-Loeb overflow. So it could happen in the past that there was some Roche-Loeb overflow, or basically some changes of material, loss of material, and we should see it in disk and wing traces. So we started to investigate if it's possible that the changes, the dips that we see in the light curves are related to this kind of scenario. But actually, we don't see any emission lines and any IR axis in spectra, which means that there is probably nothing in this case happened in the past. So we started also to investigate if it's possible to see that these dips, these changes in the light curves are related to the eclipse of a secondary star, well, primary star by a secondary star. And when you look at the animation, you see that the only possible moment when it happens, the eclipse could happen right now, which is before the heartbeat phase. So basically, we wanted to have it here. The second plot is a light curve. So it is not an eclipse. So because eclipse could happen only before the maximum phase of this heartbeat. So we still don't know what's going on. Apologize. Okay. So we started to also play with a MESA binary model. So there are also some options that there were no mass transfer scenario, or the system had to be born in an eccentricity of around 0.9 with an orbital period of 5,000 days. We also started to investigate if a star is an RGB or rather an AGB star. It's rather an RGB star. And actually, we started also to investigate some additional mechanisms, if that was possible, maybe that there was some eccentricity pumping, but actually, we started to work on it, also assuming that the primary star was higher than, mass was higher than 2 solar masses, and it turns out that there is no need for eccentricity pumping mechanism, so no additional mechanisms are required. And actually, for now, it's still a lot of open questions for that system. There is a slight change, although not very big chances, that the secondary component is a compact object. But we find this way actually to searching for or studying these heartbeat stars a great way to find also compact components. That is a plot that Kasia Kruszyńska was actually showing, and Łukasz was also showing it with the masses of compact objects, and it's getting more and more populated, and we believe that we can populate it more with the secondary components of heartbeat stars. So with this, I will thank you, and I'll be happy to answer questions.
Thank you, Milena. Are there any questions? Maya?
Okay, hello. Can I be heard from Zoom? Very nice and exciting, and your work looks really comprehensive. I think it's kind of an obvious question, and sorry if I have missed that, but could some of the dips or brightnesses could be related to microlensing by the compact companion?
Well, that cannot be actually. I haven't investigated that.
I mean, of course, it's obvious question coming from a microlensing person.
Yeah. I'm wondering. So because actually we see it. So why we could see it only in some phases? Then why not always?
And is it always the case?
Yeah. So
some of them are more...
Yeah. So basically, if we, okay, I don't know, we can get
No.
back to the.
I'm seeing the chat,
Okay,
so I
so,
cannot have both. Sorry.
Okay, so basically we see it sometimes, and sometimes we don't see it, and it's not like we see that that we haven't seen it and now we see it, but actually it changes. So sometimes it's there, and sometimes it's not there. So it's not very periodic in a sense that well, it's not in a time. It's not like it's not like it's there and then it's not there, but it's there. It's not there, then it's there, and so on, so on. So I'm wondering if with a microlensing it wouldn't be probably possible. I guess.
True.
Yeah.
But a follow-up question is: are some of the system more regular? So, for example, the brightness increase is always there, or are all of them a bit chaotic? Or
no, this is the only one that we investigated that we see these changes in dips. Normally, they are either when we compare it with the models, sometimes they are like deeper or brighter. But we believe that the model is not perfect because model is like it's a kind of simple model, I would say, analytic model. So in these cases, we believe that's the problem with the model. We should have it more like more complicated. But this is the only case we saw this changing dips, and that's why it's kind of confusing, I would say. So, but that's an interesting, actually, idea to check microlensing options for this kind of systems. Thank you.
Thank you. Any more questions? Okay, there's a question on Zoom.
Valerio Boccia is asking, are there any signs of magnetic activity in the spectra? Could these be useful to further characterize the inclination?
Magnetic activity in a spectra, meaning special lines, right? Special emission. Zeeman splitting. We haven't looked on that. Is it obvious to look at? And I'm just open. We haven't checked it. So answering questions, we haven't checked it.
I think not with that resolution, not for such faint stars.
Okay, so yeah, that could be a good comment from Pawel Zielinski, who is here. That actually the highest resolution that we have for it for the system is around 12,000, and the signal to noise there in this spectra is around 30, I would say. So I don't know if that would be possible to actually no. Staszek Zoa is also saying no. So yeah, so probably no. Thank you for the question.
Okay, Karolina.
You have dozens of stars from Ogla. Those are big stars. And what would be the criteria to pick objects to the spectroscopy survey? Because it's obvious that you will not deal with all these.
Yeah, that's a very good question. We're also actually struggling with that, especially because Ogle targets are pretty faint. And the field, especially the bulge, galactic bulge field, is pretty dense, so it's demanding to have it. So basically, we decided to track those that have high eccentricity and high and with some estimation of the mass of the primary that we could see from color magnitude diagram where they are more or less. Those of them that have massive components. So we actually get some information about with the estimation of the primary mass, we can get some information about the secondary. Those are the ones that we pick, like the more massive secondaries and also the one with the highest eccentricities.
Great. So think about also maybe for the magnetic systems or more magnetic systems for the polarimetry.
But they are too faint. These are too faint.
But even depending what you need, you can reach over 50 magnitudes. So if you find objects for spectroscopy,
yeah, we have some candidates from galactic disk which are brighter. Yes, so yeah. And another thing is that we also have like a bunch of test data that we are investigating right now, which are brighter. So we'll do so. Thank you.
Okay, let's move further discussion to the Slack channel. Thank you once again, Milena. And now we're going to have a talk from Piotr Kolanderski from...
I'm afraid not yet.
Not yet, still not connected.
He's connected, but we're having problems. So
Okay, I see. So
I will wait for his slides, but could we have Fatima now?
yes, so we're going to have a talk from Fatima Teska from Atatürk University about exoplanet transit timing. Small
You
telescopes.
prefer PDF or PowerPoint?
Yeah,
Which one?
PowerPoint. Yeah.
I'll try the PowerPoint. Let's see.
Okay. Doesn't have PDF. It's okay.
Let's see if this opens, then it's fine.
Okay. I am Fatma Tezcan from Atatürk University in Turkey. I am in the 5th month in my PhD, and
Just a second.
thank you very much this precious chance. I am happy to be here.
So this
Okay.
you're in charge.
I talk about the exoplanet observation with transit timing variation with small telescopes. We begin with our working group. Begin the question the existence of the other objects that are gravitational bound of the planetary system, and which were previously determined to have planets, but that could not be detected by any other method. This method is based on the planet's periodic variation in transit time. If transit of the planet bound to the system is not visible or its transit cannot be observed due to observational deficiencies, due to the gravitational effect of the star on the planets whose transit we observe, change in transit times due to the perturbation effect and light time effect. And as you can see, Atatürk University ATA50 telescope, we start to observe some selected object using the ATA50 East 60, Uzaymer 50, Kraken 35, and T40 telescopes. I would talk about the Qatar 1b exoplanets observations. Most important criterion for observations is the determinant of the exposure time. While determining the exposure time, we kept the exposure time high so that the scattering is reduced. In addition, although the high exposure time reduced the scattering, it can be increased to a certain limit in order to not to be exposed to saturation. And keeping the exposure time high will reduce photon noise and increase the signal to noise ratio. In addition, the scintillation effect caused by the Earth atmosphere in the ground-based observations is reduced to some extent with a long exposure time. Using the long exposure time causes the signal to noise ratio to be dominated by the photon noise. And in this case, the problem can be overcome by taking the telescope autofocus. In this way, even for bright stars, high exposure times can be used. For this reason, the focus observations technique has been applied in the transit observations of the Qatar 1b exoplanets. Yeah. Astronomy was used to analyze the data obtained from the observations and in order to minimize the air mass effect and the observations time converted to dynamical barycentric Julian day. And there is our observations, Qatar 1b transit light curve. Red points are light curve and error normalized to non-transiting light level, and green continuous curve is air mass change. And in addition to the observations, the acquisition and modeling of light curves from exoplanet transit database, literature, and tests and exoclock, yes, will include all the observations of the objects so far. It is important for us to understand that whether will be change the transit timing variation over time. There are the exoplanet transit database, literature, exoclock, and TESS transit light curve. And after the astronomy transit models, mid-transit times were calculated. The variation in the collected minimum times was examined. Reference values were taken from the Collins et al.'s paper. And then, by using the Python script and necessary modules, the least squares minimization was made the most suitable linear fit was applied to data. As you can see, least squares minimization. And then TTV analysis was performed on the same data set with the MCMC algorithm, and results were checked. In order to evaluate which of the linear and quadratic fit we obtain is more suitable for the model, the reduced chi-square value was obtained as a result of the application. And the large number of parameters of the model, as you can see, the linear and quadratic fit application results. Chi-square, there is the chi-square formula. The chi-square value tells us how many sigma distance on average the model has passed from the data. And the reduced chi-square is obtained by dividing this by the degrees of freedom. And so you introduce model complexity, since the degree of freedom is the difference between the number of points and the number of parameters of the model. While the reduced chi-square values obtained for Qatar 1b are very close, the linear fit with the smaller chi-square will be superior. The large number of the parameters of the model reduce the degree of freedom and enlarges the reduced chi-square, creating a bias against multi-parameter model. Actually, this is a philosophical approach, which is also suitable for the Occam's razor approach, which is expressed in the simple model with favored parameters, is a valid among the models that can explain the same phenomenon with similar performance. Therefore, we make the comparison between linear and quadratic model and two models over the reduced chi-square. The closer the reduced chi-square is to 1, the more successful model, because it means that the model can explain 1 sigma deviation. In addition, chi-square values, AKK information criterion and Bayesian information criterion were obtained. These values, just like chi-square, they say the model's closeness to the data points as a success. The smaller distance, the smaller this criterion take. And then after the linear and quadratic fit, a periodic change was started to be questioned with the Lomskargl algorithm for the mid-transit times for our data set. And then we resolve a cycle 470 days, 470 days with a false alarm probability 0.021 at the dominant frequency is observed. And then there's I'm sorry for a plot language, I forgot. X-axis the cycle transit timing variation, representation of the obtained dominant frequency period on the data set, the left plot. The right plot, change of the dominant frequency cycle on the data set by a phase. And then sinusoidal fit was made to determine sinusoidal change to find the errors, the parameters, and result. A negative parameters may mean that the period is decreasing. The reason for the decrease is the period could be 30 body effect, could be star and planet are getting closer to their star by losing angular momentum as a result of the tidal interactions, and could be star may have magnetic activity. When the results don't make any sense at the moment, more observations data is needed for more precise results. We are planning to continue observations to check for the other planets in the system. And I would like to finish my verse Eastern Anatolia Observatory, Doğu Anadolu Gözlemevi. Doğu Anadolu Gözlemevi 4-meter class visual and near infrared class telescopes. It has an adaptive optic, and at 3,170 meters in elevation in Erzurum in Turkey, and you can see Oftak on map here, and the 50 telescope will be replaced to in the of the Daxite near the Daxite. Thank you very much. Thank you for listening.
Thank you very much, Verma. As we are a bit behind schedule, I think we'll move the questions to Slack. Have we solved the technical problems there?
I hope so, but we can have
okay,
one question.
so in the meantime, if we have some questions,
I just have a very quick one. Just a quick question. The 4-meter telescope, is it already operational, or when is it going to be active?
Almost 3 months. Okay. The Eastern Anatolia Observatory, right?
Mm-hmm.
Yeah. Almost 3 months later, we'll start the calibration and test observations. Actually, in addition, my PhD subject is a observe the exoplanet with coronagraph. Yeah, in 4-meter telescope, telescopes.
Okay.
Yeah.
Very nice.
Okay, thank you. Are we ready for the next talk?
Right.
Thank you once again, Verma. We can hear you, but there is a lot of delay. Okay, it's better now. So the next speaker will be Nicolaus Copernicus, who will talk about quantum communication with a satellite link. Can you share your screen?
No, he's not going to share the screen.
Okay,
I'm trying to open the PowerPoint. Just a second. Oh no, he's sharing. No. Piotr, can you try sharing again?
Okay.
Can you try sharing? This is what happened.
Okay. Does it work now?
No.
No. Okay. So Łukasz, if you could help me with that, I will just talk.
Yeah, I'm trying. No. Just a moment.
Okay.
Right. Right. So tell me when to switch the slide.
So. Okay, great. I'm assuming that you can hear me clearly. So my name is Piotr Konderski. I work at Nicolaus Copernicus University, at which we have a lab. And there is a couple of it's called Single Photon Applications Laboratory. Next, please. Okay, great. So this laboratory is in Poland, as you can, and the nice panorama of Torun, and on the right corner there is a half of the lab. Next slide, please.
Oops.
Okay, so let's skip this slide because maybe the quality is not good, but that's just okay. So in single photon applications laboratory, we work on actually two main things. One is quantum communication, and actually we work in fiber on fibers and also satellite links. And the other thing is more fundamental. This is photon-atom interaction. For this talk, I will focus mainly on satellite links. Next slide, please. Okay, so what is the motivation? So I'm not astronomer, so I have, let's say, more simple motivations for my work. So cryptography is one of the motivations. So the main setting, or let's say main idea that we can have in mind is depicted here. So let's assume there is Alice and Bob, and they want to share message. So Alice wants to send message to Bob, and she wants to encrypt this message. So the thing is that they need to have a key or two keys in order to encrypt their message. Typically, if those two keys, KA and KB, are the same, they have absolute security, because if no one else except them knows that key, then everything is okay. Next slide, please. Okay, perfect. So quantum communication is all about exchanging keys, not messages. So Alice and Bob first, they have established key, and the way we help with that is by using photons. Next slide, please. Okay, so how can we establish a key? So Alice needs to send information to that information to Bob in a way such that no one else can learn about this key. So typically we use single photons. So we can imagine pulses of light which contain only one photon. And in that one photon, we can encode information. So for example, we can use polarization encoding. So let's say horizontal polarization can be 1, and vertical polarization can be defined as 0. So the fundamental theorem by quantum mechanics says that there is no way to clone two quantum states. So we cannot measure a photon and replicate it. So this is the basis of the security. Okay, next slide, please. We are approaching to the satellites. Okay, so talking about light, which is let's consider 500 kilometers above, and we have two ground, S1 and S2. Next slide, please. Okay, how does it work? So let's assume, let's look first at the on the left part of the picture. So satellite flies over a optical ground station S1, and it exchanges key or establishes key between S1 and itself. So then it flies over another ground station on which we have Bob. So in quantum communication, we always talk about Alice and Bob who wants to communicate, and there is Eve, like eavesdropper, who wants to intercept key or message. So here, the satellite establishes another key with Bob, and then they can combine safely those two keys, and the resulting key is known only to Alice and Bob. So how can we do that? So we need to have a transmitter on a satellite which is able to send single photons to the ground station, and we also need an optical ground station which is able to receive and detect single photons. There is two kinds of quantum communication. One is based on a single photon, and the other one is based on photon pairs. So this one is a single photon version. Next slide, please. Okay, so how can we generate entangled photon pairs? So the basic phenomenon is called spontaneous parametric conversion. On the left side, you can see experimental, very simple experimental realization. So we have a tiny nonlinear crystal. We illuminate it with a laser beam, and then from time to time, we get photon pairs. So on the left side, you can see in the middle a nonlinear crystal. This is the thing which is depicted and labeled by height 2. To that crystal is illuminated with the pulse, and we have two photons, S and Y and I, which travel to Alice and Bob. Next slide, please. Okay, so Alice and Bob are somewhere. Next slide, please. Okay, great. So there is SAGA project, which is an acronym from Security and Cryptographic Mission by European Space Agency. And the idea is that such a source can be mounted on a geostationary, on the satellite on GEO. And one photon can be sent to one optical ground station and the other photon to the other optical ground station. So why it is like that? So quantum mechanics says that if we have such a source of two photons, then we can prepare it in such a way such that, for example, if Alice is in Brussels and Bob is in Warsaw, then the satellite can be delivered by or provided by another party, for example, from Russia or China, and we don't really have to trust the satellite in order to have a secure key. And again, this is a version of quantum communication which relies on two photons. Next slide, please. Okay, so so far there was only one demonstration, experimental demonstration of such a setting. It was done by a Chinese group. So the satellite demonstrated single photon version and two photon version of these kind of protocols. So they could establish a key between two ground stations in China and one ground station in Europe, and they used that key to communicate with each other over, let's say, classical internet. Next slide, please. Okay, so what are the projects at Nicolaus Copernicus University? So the first one is in a collaboration with Center for Astronomy in Warsaw. So this is a collaboration with Maciej Konacki. He's gonna have a 1 meter telescope in South Africa, and we will use this telescope also to show that uplink quantum communication is possible. So this is a version of quantum communication which is based on two photons. So we provide, my university, my group provides a source for that project. So 785 nanometers photon is gonna be transmitted fiber. Next slide, please. Okay, so this is a setup that we have in our lab. So it's a little bit complicated as compared to what I presented at the beginning. So I'm not gonna go into details, but you can see that we pump with a, let's say, a classic 532 nanometers laser, which is cheap and reliable. And then we generate two photons. On the bottom, you can see idler photon at 1651 and signal at 785. So 785 is going to be shoot to the next slide, please. Can I have next slide? Okay, and the next project is devoted to electronic control for entangled faults, a collaboration with Sydera Polska from Gdańsk and Gdańsk University. So here the idea is to develop an electronic controller which can be used for geo satellite. And we provided a photon per source. So the company is testing the electronics on our source. So the electronics is gonna be space grade, and the source, the optical part, is just a simulator. Next slide, please. Okay, that's almost okay. So forget about the goal, which is not displaying properly. But the other another project, the last one that I'm going is by European Space, and we do that for European Space Agency, and this is in collaboration again with Sydera Polska and Work Microwave from Germany, and this is related to ranging for optical communication terminals. So there is that idea to replace or supplement classical communication between, let's say, ground station and satellite, which is based on radio frequency, with optical terminals. And if you have optical terminals, you can also you can communicate, of course, but you can also measure the distance between the ground station and the satellite almost simultaneously with a communication. So instead of laser ranging, you can do this kind of optical ranging almost in the same time as you communicate. The next slide, please. Oh, this one does not really look good. Okay, so this is the last slide. It was gonna show it was gonna show my supporters and the project and also the team. So maybe let's skip this one. So with that, thank you for your attention.
Thank you very much, Piotr. And have just one quick question. Milena?
Thank you. As a group of astronomers, we are actually interested mostly in a sensor, so telescope, this 1 meter telescope in South Africa. Could you comment on it, if it's already working and if it's possible to use it for some scientific cases like time domain astronomy?
Okay, so this is the part which Maciej Konacki is responsible for. This telescope is not working yet. As far as I remember, yeah, the basis of the telescope is already there, and there is two purposes of that telescope. One is for the space debris monitoring, and the other one is, let's say, collaboration with me for quantum communication with LEO satellites. So this is a good question. I think I'm sure that Maciej Konacki is gonna be able to respond.
Thank you very much, Piotr. And fingers crossed for the operation of the telescope. If you have some further questions, please ask them. Next slide,